Hey, what up guys? So same as last time, right? We're gonna find our x vector, displacements and slopes. And then as soon as you find that as x vector, because at the end of the day it's just forces equal to kx, right? So find the x vector, then find the force vector, and then you can find the forces in each elements, and then we'll just draw the shear and bending. You know, this problem took me a while to make. The video's pretty long, but the less comments I get about, hey, for this, blah, 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 you got this, I got this, why? I try to be as detailed as possible, so to avoid those comments, I try to explain every single thing along the way, and I hope it makes sense. So let's go ahead and get started. All right, so we start with the stiffness matrix for every element, right? Every element's gonna have a certain stiffness, and that's what this K matrix is telling us. This is just from the chapter itself. You should be able to get it from your professor's notes, all that good stuff. You start with the boundary conditions. So there's 2 degrees of freedom for every node, and we have 3 nodes, right? 1, 2, and 3. So that means 2 degrees of freedom, 3 nodes. That means you're gonna have 6 total degrees of freedom. You're gonna have a 6x6 global equation, a 6x1 force vector, and a 6x1 displacement vector. Because at the end of the day, right, it's just force is equal to kx. You find your x vector, which is just your displacements and slopes at nodes. And then as soon as you get that, you find your force vector, which is your reactions. Once you have all that, you should be able to find your forces in each element. And then finally, you could draw the shear and bending diagrams. So with the boundary conditions, right, step 1, in this case, we're gonna have V1, V1, V2, let's put V2, right? And then V3, V3, okay? So I've said it multiple times in other videos. If you know one, you don't know the other. So you either know the boundary condition or you know the force or moment, but you don't know both, and you never not know one, okay? So V1, it's a fixed location. So that means no matter how much force you put anywhere along the beam, that's not going anywhere. So V1, displacement in the y direction, is 0. And then phi1, right, the angle it makes with respect to the x-axis is always going to be 0. So you know that from statics, no big deal. Boom. V2, if you apply a force, the problem's saying that there's a 0.5 inch gap. So that means it's going to move 0.5 inches. And if it's going to want to keep moving more, then, I mean, it doesn't matter, right? The most it's ever going to move is 0.5 inches. So that is going to be a negative 0.5, okay? And don't worry about the units, no big deal. And then displacement, there is going to be some there is going to be some angle, right, that it's going to form with the x-axis. We don't know that, so let's put question mark. V3, it's going to displace an amount if you apply 500, so we're going to put question mark because we don't know that, and then it's going to make an angle. So in this case, we know 3 boundary conditions, so that means we must know 3 forces or moments in this, and this is how we're going to do it, right? So step 2 is your global equation. All right, so this is just your forces equal to kx, right? We're going to have F1y, M1, F2y, M2, F3y, M3, okay? And then we're just using this, right? The stiffness matrix, it's the global stiffness matrix. So we got to incorporate every element. We need to know what's EI over L cubed. In this case, we're going to keep everything in inches, right? Because E is given as 30 times 10 to the 6 PSI. I is equal to 200 inches to the 4th. So we're going to convert these. 20 feet is 240 inches. Okay, so every element is 240 inches, and that's the number we're going to use for EI over L cubed. Okay, so I'll go ahead and give you guys that number. Feel free to verify it, but if you get something different, that means you're wrong, no offense. But it's 434 pounds per inch, and pounds per inch is the right unit, right? It's a stiffness. We're gonna put 434 right here, and that number should be the same for every element. In this case, because they're the same length, we could just factor that out of the global stiffness matrix. If not, I mean, this could have been 20 feet, this could have been 10 feet, so it's not recommended to do over L cubed. It's better to put the L cubed in the matrix and multiply L to every single element, and you'll just have EI over here, okay? Just keep that in mind. They might trick you with that, but in this case, the problem's symmetrical. It's 20 and 20, cool, we're perfect. Okay, let's go ahead and label the matrix V1, Phi1, V2, Phi2, V3, Phi3, okay? And we could do the same thing going this way, V1, ooh, it's tight space, V1, Phi1, V2, Phi2, V3, Phi3, okay? So this is our global stiffness matrix, and we'll fill it out in a second. And then our displacement vector, this is just V1, Phi1, V2, Phi2. You'll see it in a second, V3, Phi3, okay? Boom. So we know some of these. We should know some of these. Let's fill it out. But before, let's fill out this stiffness matrix, okay? So all I'm going to do is use this stiffness matrix here for every single element. In this case, we have two elements, right? This 20-footer and this 20-footer. This 20-footer is between nodes 1 and 2. So that means this 4x4 matrix is going to go here, right? V1, Phi1, V2, Phi2. And then V1, Phi1, V2, Phi2. So this 4x4 section right here, that's going to be that element. And then the next one, 2 to 3, is going to be this 4x4. I'm sorry. V2 to Phi3 over here. V2 to Phi3 over here, right? Because it's between nodes 2 and 3. So that's going to go in this 4x4 matrix here, okay? And the other ones are just going to get zeros, those two little gaps. So let's go ahead and do that. It's going to be 12 4L squared, 12 4L squared, right? I'm just copying this into this. 6L, negative 6L, negative 6L. And make sure you carefully do this because it's real easy to mess up. It's symmetrical, right? So I'm just gonna, the rows become columns. 6L, negative 12, 6L, negative 6L, 2L squared, and negative 6L. Okay, that 4x4 matrix came into this, okay? All right, now let's go ahead and do the same thing for element 2 now, between node 2 and 3. So 12 gets added to this 12, and then 6L gets added to both of these. It's symmetrical, right? So that's also a 6L. And let me use my pencil. This spot here is a 6L because it's symmetrical. So these two go to 0. This will be 24. And then 4L squared, that's going to be 8L squared. And then I'm also just going to fill the remaining part of the matrix, okay? All right, so I want to go ahead and edit it, right? I just put this little stiffness matrix here, no big deal. And the rest becomes 0, right? Double check the numbers. I'm doing this problem as I go, but the numbers I do give you, like the answers, they are correct. But it's kind of hard to, I already did the problem, but I could make slight errors here, but don't worry, at the end of the day, the answers are correct. So, just do that at least, right? Just double check everything. Okay, now let's go ahead and fill in what we know, what we don't know. In this case, we know V1, Phi1, and Phi2, right? So the top three. Let's go ahead and insert those in. And this is what I mean when I said earlier that if you know one, you don't know the other, and vice versa. So because we know these three, that means we don't know these three, okay? And because we don't know these three, that means we know these three. So I'm gonna go ahead and that's the trick, right? If you're having trouble with this class, knowing that little trick is gonna save your life. And if you're in the exam and you think you know both of them, that means you did something wrong, just FYI. But you either know one or the other, but you never know both, and you never not know one. Hopefully that makes sense. Let's look at node 2, the rotation wise, that's the moment component. There's 0 moment being produced here, okay? So that means this is gonna be 0. They would have given you like a rotating arrow if that was the case. That's how you know you would have known it. But in this case, nothing's given, so it's 0, right? V3, yeah, we know negative 500 is coming down. So that is negative 500. And then moment 3, 0 moment. So boom, just like that. F2y, when you push this down, this roller here is gonna push it back up with a certain force. So we don't know it. Moment 1, you know from statics on a fixed support, there's a moment reaction and there's a force reaction, right? So F1 and M1. Well, we already knew that because we knew these numbers, so we already know we don't know these numbers, okay? So again, once you get to that spot, we're good. Now we're just gonna go ahead and step 3, systems of equations. systems of equations. We're gonna formulate equations. In this case, we have 6 equations, 6 unknowns, okay? We know all of this, L squared, we just know it's, what do you call it, 240? So all these are numbers here, technically. You see L, but it's all technically numbers. And earlier when I said L cubed, when you have different size elements, you'll want to throw it in there. So 12 divided by, actually, hold on. Yeah, so in this case, if you know L in this case, right, but it could vary between every element, so you'll probably have to throw this in sometimes. This is just K is equal to a constant over L cubed times, let's just assume another constant, right? So you can either divide this constant by L cubed or this one by L cubed. So if K, right, K is equal to, in this case, EI times all your matrix, you have to divide everything in the matrix by L cubed, if that makes sense. So 12 divided by L cubed, 6L divided by L cubed. All these numbers divided by L cubed. That's only if your elements vary in size. If they don't, no big deal. You can just pull it out and keep it outside, okay? Like we did here. And my bad, this is L cubed. There you go. Boom. All right. So equations, right? When you have zeros, you can go ahead and cross out the rows for that column. So what we're going to do is this. V1 is 0. So you cross out that row and you cross out that column. My bad. Cross out that column, cross out that row. Same thing with Phi1, right? Phi1 is 0. So these go away. And that's about it, right? You can't cross that one out because that's a number. Phi2, V3, Phi3. It's a 4x4 matrix. In this case, we're going to solve for 4 unknowns, F2Y, Phi2, V3, Phi3. And then, yeah, that's pretty much it, right? It's just algebra at this point. So let me go ahead and assemble the equations. I'll walk you through it, but let me go ahead and assemble them first. All right, so these are the equations. Let's start off with the first one. I just wrote them down to save time. F2Y is equal to 434 times, parentheses, right, open parentheses, 24 times V2. Or let me just do it this way. It would have been negative 12 times 0, but that's 0, right? Negative 6L times 0 plus 24 times this, negative 0.5, plus 0 times V2 minus 12 times V3 plus 6L times Phi3. And that's what I got here, okay? F2Y is equal to 434 minus 12 minus 12V3 plus 6L Phi3. I just got rid of the zeros. Next one is 0, same thing, right? These go away because we already crossed them out, so don't worry about them. 0 is equal to 434 times 0 V2, 8L squared Phi2 minus 6L V3, 2L squared Phi3. And boom, that's what I got here. Same thing with this one. Negative 500 is equal to 434. In this case, I just divided by it already, right? Negative 500 over 434 is equal to negative 12 times this minus 6L times Phi2, 12 times V3 minus 6L times Phi3. That's what I got here, okay? And then finally, 0 is equal to 6L V2. 6L V2 is negative 0.5. That's a number, so that's going to give you negative 3L. 2L squared Phi2 minus 6L V3 plus 4L squared Phi3. Okay? Now, I'm going to go ahead and just simplify these equations. I'm not going to do anything crazy, but I'm going to put them in a systems of equation format. All right, so that's all I did. I just reorganized the equations, and in this case, it's a 4x4, right? I mean, you have 4 equations and 4 unknowns. Your unknowns are F2Y, Phi2, V3, and Phi3, right? So what you can do, right, after you do the organization, right, move all the constants to the side. In this case, 12, 0, negative 7.15, and 3. And move all your variables to the side. Phi2, V3, Phi3, and F2Y. I mean, you don't see it here, but technically this is a 4x4, right? I mean, it's a V3, negative 12 V3 plus 6L Phi3. It's probably plus 0 Phi2, right? There's a 0 Phi2 somewhere. And then minus this number F2Y, 0.0023 F2Y. And there's a 0 F2Y here, 0 F2Y here, 0 F2Y here. And using, what do you call those calculators? The fancy ones, the graphic calculators, whatever, the graphing calculators, you should be able to easily find your 4 equations, your 4 unknowns, right? So your professor might not let you use it. What you could do is just basic algebra, right? Get 2 equations, whichever ones you want. In this case, And look, before I go into that part, this one's the only one with f2y. So this is 3 equations, 3 unknowns right here. Just forget the first equation. You could solve 3 equations, 3 unknowns, and then get those 3 numbers and you plug it into here, v3, phi3. In this case, there's no phi2. And then you'll find f2y, okay? So you could do a 3x3 if you want, or just do the whole 4x4. They'll give you the same answers, and that's kind of what I did here. I just got a calculator online, right? I plugged in my numbers. In this case, the first thing I did was a 3x3. Same thing, right? I multiplied those L numbers that you saw just a couple seconds ago, right? 8L, 2L, 4L. L is just 240 inches. So that's why those numbers you don't see them in my write-up right before this, right? But that's all it is. Just 3 equations, 3 unknowns, and boom, you can see those are the answers. Now here's a 4x4. So the 4x4 is incorporating that f2y, but it's the same thing. You just plug in zeros where you had f2y's in the other 3 equations, and that's what I did there. Like I said, it should give you the same numbers if you did everything correctly. As you can see, those 3 of the 4 that it found are the same ones as the previous when we did a 3x3, right? So that's all that is. That's kind of just to prove it is correct, but we'll keep going in the problem. And here are just the numbers, right? phi2 is negative 0.00432. V3 is negative 1.921. Phi3 is 0.00672 negative radians. Just the same numbers you saw on the previous slide, right? You could solve for it again now algebraically. Let me go back to that point. You'll get, in this case, if you want to do a 3x3, that's probably a little easier. You'll get these 2 equations. You'll eliminate a variable. So if you multiply the bottom by 2, everything by 2, you'll cancel out V3, right? Then once you add the 2 equations together, you'll have phi2 and phi3 equal some number, right? I mean, you'll have numbers in front of these 2 as well, but you have 2 variables, 2 equations, 2 unknowns in that case. Then you'll do the same thing except using these 2 equations, but you have to eliminate the same variable. So if you eliminated V3 in this one, you got to do the same thing here. Multiply everything to the top by 2. This will get canceled out because negative 12V3 and 12V3 once you add them together. And then whatever phi2 and phi3 give you, then you use those. So in this one, you got 1 equation, right? My bad. I said 2 equations, 2 unknowns. That's not right. You get 1 equation with 2 unknowns. And then this one will give you 1 equation with 2 unknowns. You use those 2 equations to eliminate another variable, and then you solve for 1 variable. Then out of those 2 equations that you obtained from this step and then this step, you plug it in to get the second variable. Then once you have those 2 variables, you can use any of these equations, and you'll solve for all 3 variables. Then once you have all 3, you can solve for f2y, right? So in this case, I mean, I showed you the 4x4 gave me f2y as well, but I mean, if you did the 3x3, all you have to do is get these 3 numbers and plug it into the f2y one. In this case, we only need v3 and phi3. f2y, let's go ahead and do step 4, reactions. And f2y is the first reaction that we'll get. We need to get 3 reactions, right? f2y, f1y, and m1, but f2y was very easy. You just plug in. f2y is just 600 pounds. And it might be a little off, but that's only because of rounding. I forgot what the exact numbers gave me. Again, this problem was already done. I did it at work when I get bored, right? And again, all these problems get proven. I mean, I prove them at work, but just that because of where I work, I can't bring that stuff with me. It's just in the program. Program has no idea why I even did that problem, but I did it just for this, right? f2y is 600, okay? So we're going to do the same thing we did, but now we're just going to do the f1 equation and the m1 equation. They're crossed out, but you got to keep it going, okay? So f1y is equal to 434, 12v1, 6l phi1, minus 12v2, 6l phi2, 0v3, 0 phi3. And then second equation is m1 is equal to 434, 6l v1, 4l squared phi1, minus 6l v2, 2l squared phi2, 0, 0. Okay? All right, once you do that, I just got rid of all the zeros, right? The first 2 became zeros because of these, and then the last 2 became zeros because of these 2. So you only have two little constants in each one. So plug in your phi2 for both of them. In this case, they're all just dependent on phi2. And for F1y, you will get negative 100 pounds. And then M1, you'll get 96,500 pound inch, okay? And positive means it's counterclockwise, but when you draw the shear and bending, that's not exactly the case. We'll get there when we get there. But once you get to this step, you have everything, right? You have your whole force vector, F1y, M1, F2y, M2, F3y, M3, and then you have your displacement vector, phi1, V1, I went backwards, I don't know why, V2, phi2, V3, phi3. You have everything. So we just determined displacements and slopes at nodes and then reactions. Now we're going to forces in each element, but before we get there, let's verify the numbers. Do not move forward until you verify the numbers, and it's real easy to verify them. It should take you like 20 seconds if you're good at statics, okay? And it's worth it in the exam, right? You don't want to rush it, because that's all going to determine if your forces in each elements are wrong, and then your shear and bending, okay? So it's real easy to verify. Look, you just do some of the forces in the X, some of the forces in the Y, and then the moments. In this case, there's no X, don't worry about it. Some of the forces in the Y. You have 500 pounds going down here. F2Y says positive 600, so going up. F1Y says minus 100. Does that make sense? Yeah. 500 and 100 going down, 600 going up. That's an equilibrium. Cool, we're good. Now, usually if that makes sense, that means your moments are going to make sense. That means you did everything right. If your moment doesn't make sense after your forces make sense, something's up. I don't know what happened, but that's rarely the case. If your forces make sense, that means you're good. But you could go a step further and just verify real quick. Let's go ahead and do the beam itself, what we're dealing with. We have 500 going down. You have 600 going up. You have 100 going down. And then you have a counterclockwise positive moment of 96,500. Okay. Now you want to verify that M1 does have a moment. Remember, M2 is 0, M3 is 0. So you're probably tripping like some of the moments doesn't make sense. That's not how it works. Okay, remember. Let's do basic statics and just take a moment about point 1. Okay, node 1. 600 is doing a negative moment, right? Oh, I'm sorry, counterclockwise, so that's positive. 600 times 240, okay? 600 times 240, and that is positive, okay? Then 500 is doing a clockwise moment. So that means it's a negative 500 times the distance is 480, okay? 20 plus 20, that's 40 feet, times 12 inches each feet, that's 480, okay? And then you just add the moment, plus 96,500. Okay? And because, all this, give me a second, I'm not sure if I'm wording this correctly. But when you do this, technically, hold on. It's 96,500, okay? But you don't write that because you don't know it. You're verifying it. My bad, I went a little too quick. This is just a reaction. MA. Okay? So the whole point of this is solving for MA. So no, putting 96,500 there doesn't make sense because it's going to work, obviously. So all this has to equal 0, right? It's an equilibrium. And if you do the math, yeah, it does. 96,500 is equal to MA, right? Your MA is indeed equal to that, okay? This is a very big number, right? Although 600 is bigger, 480 is way bigger than 240. So it's going to be a positive. This is going to bring it down some. That's going to be 96,500. And you can verify on the calculator. So you see, just like that, we verified. We're good. So once you do that, we're going to go ahead and do the forces in each element. And we already verified this, so we're safe to do so. Let's go ahead and do that, right? Step number, what step was that? Step 9. Forces. Step 5, I'm sorry. In each element. So step 5, forces in each element. That looks ugly, but whatever. Okay, it doesn't matter. Let's do element 1, okay? In this case, it's one element, so we're gonna have 4, it's gonna have, look, F1Y, M1, F2y, M2, okay? It's gonna equal the what do you call it, the stiffness of that element, which we already determined EI over L cubed was 434, and that is between nodes V1, Phi1, V2, Phi2, okay? And then V1, Phi1, V2, Phi2. Boom, okay? And that stiffness matrix is nothing but this stiffness matrix right here, okay? So I don't want you to get these numbers, 24 and 8L squared, 0, 0. No, you're gonna have to get these right here, okay? Don't forget about this matrix, we're done with it. So now let's go here. We're gonna get 12, 4L squared, 12, 4L squared, 6L minus 6L minus 6L. Let's do minus 6L minus 6L 6L, right? Minus 12 6L, and then 2L squared, and then we're gonna put minus 12 6L 2L squared, and then the vector, right? V1 Phi1, V2 Phi2. In this case we already found them. We're just gonna go ahead and plug them in, right? We already found all these and all these. So Phi2, Phi3, V3, and 0, 0, negative 0.5. It's V1, Phi1, V2, Phi2, okay? So that's gonna be, let's do this number first, it's pretty big. 3, 2, minus 0 0.5, 0, and 0. Okay, that's your vector. And just do the same thing we did on the global equation, just with this little 4x4. I'll go ahead and do this one for you guys, and then you guys do the second one on your own. You're gonna have 4 equations, 4 unknowns, right? So, but this one's not that bad because you already know everything. You're just plugging and chugging. So 434, and then you're gonna have 6 minus 6.2208. Okay, that's for F1y. It's 12 times 0, 6L times 0, minus 12 times negative 0.5, which is 6. And then 6L times Phi2, okay? So in this case, we know L is just 240. So we know all this, okay? And we know all of this, so that means we should know all of this. So that's the setup right there. M1 is gonna be 434, 720 minus, oh my bad, this is a 497. 497.664. F2y is gonna be 434 minus 6 plus 6.2208, and then equals, this one's gonna be 434 720 minus 995.33. Once you do the plug and chugging, all right, we're gonna get these numbers right here. F1y is equal to negative 100 pounds. M1 is equal to 96,500 pound inch. F2y is equal to 100 pounds. M2 is equal to minus 120,000 pound inch. So again, this is just the forces in the element. It doesn't mean it's our global force vector, okay? Now, we'll verify this at the end. Once you do every single element, in this case we have 2 elements, but this is how you verify it. You cannot do it just yet. Let me go ahead and do the second one for you guys, and then same steps, right? But we'll verify it right after. All right, once you do all that, this is the second element, right? It goes from V2 Phi2 to V3 Phi3. So V2 Phi2, V3 Phi3, and V2 Phi2, V3 Phi3, you know them, same as you did here, but now look, these two kind of shifted up, if you could notice from this. But L, you know, it's just the length, it's just 240, okay? So you could go ahead and plug it in here, or you could wait until you actually like break it out here. In this case, I didn't do it, but I'll show you I did at the end. But this is how you would verify it, okay? In this case, you already found all your force elements, right? This is the second element. We're done. Let's do that. Oh no, I just want to box them up, right? And then check this out. This is how you verify these. When you add all of the same, in this case, all of the F1Ys, all of the M1s, all of the F2Ys, whatever, you should get your big F2Y, your big F1Y, your big M1, your big M2, all that good stuff. So let me show you what I mean. Get all your F1Ys, in this case, it's out of these four and these four, get all the F1Ys. We only have one. It's negative 100. That should be equal to the big F1, okay? The big F1 over here. And yeah, that big F1 was equal to negative 100. The M1, same thing. Get all the M1s. In this case, we only have this one. Out of all the 8 of them, right? 96,500. And that equals your 96,500 here, okay? So do the same thing for all of them. F2 is the only one that kind of overlaps, right? I mean, F3 and M3, there's no other one. So negative 500 and 0. Yeah, 0 moment, negative 500. That's what's happening right there, right? We already determined that. F2Ys are the ones that vary. F2Y is 100 here and 500 here, okay? So that means combine them, you get 600. That should be equal to your F2Y, 600. And then your M2, negative 120,000 plus 120,000. That means add them up, you get 0. And yeah, your M2 is 0, right? No moment is acting on it. Again, this one's, by the way, this wasn't 0, but all of these numbers are rounded. I mean, to the decimal points, you're gonna get some number, right? I think this number was like 100 something. I can't remember. I did it like a couple days ago, but relative to 120,000, that's 0. So that's the trick to it, right? I don't want you to get a number like, oh, how did I get negative 300? I mean, negative 300 to 120,000 is just a rounding error, right? So no big deal. Finally, we're done with that. We're just gonna go to step 6. Final step, shear and bending. Okay, let's go ahead and do the shear diagram. I'm gonna try to do this very neat. I don't like not being neat, except when I'm in a rush, right? As you've seen in some of this writing. But okay, let's do shear. That's gonna be in pounds, and let's do moments over here. And I know you're probably wondering, I mean, why am I adding more space here and less space here, right? It's because I already know what the answer is, but I mean, if you don't, try not to give one side too much room. You got to know which side's going to be a bigger side, right? In this case, I know this moment's going to be, it's positive because it's counterclockwise here, right? It's positive. But when you do the bending diagram, that's what I meant earlier when I said it, when I got this number, it brings you down on the bending diagram. So I know a lot of the chunk is going to happen here for bending. Shear, 100's pushing me down, nothing happens, nothing happens, nothing happens. 600 pushes me up, nothing happens, nothing happens, nothing happens. 500 pushes me down. So at the top, I'm going to have like 500 shaded area, right here 100. So I'm going to give the top more room, okay? Try to draw them as like to scale as possible. You might not be able to, but most professors are cool about it. As long as you get the numbers right, you should be good. So let's go ahead and do the shear diagram. I just did it here for you guys, if you heard me say it right. Minus 100, then nothing happens, nothing happens, nothing happens, nothing happens. 600 pushes you up, so now you're positive 500, because you are negative 100, right? So now 600 pushes you up, and positive 500, positive, positive, positive. Negative 500 brings you down, you're back at 0. So that's what the shear diagram looks like. Let's go ahead and put negative 100, and let's do 500, and it's all pounds. So 100 pushes you down. It's like halfway throughout the beam, right? Let's do that. This is halfway throughout the beam. So this is the trick. 100 pushes you down, nothing happens, nothing happens, nothing happens, nothing happens. 600 pushes you up at the middle of the beam. Boom. Nothing happens, nothing happens, nothing happens. 500 brings you back down to 0. Okay? And boom. So just like that, we know this is 0. This is 240 inches. And this is 240. Okay? So that's what the shear diagram looks like, okay? So let's go ahead and shade it in. I like to be a little creative with it, right? Boom, boom, boom. Make it look nice. You might not have time for this on the exam, right? This just should be your last step. Shading stuff in. But this is how you find the bending diagram. Now we're done with the shear. That's it. That's all there is to it. There's just 3 shears acting on it that wants to slice your beam in half or whatever. So check this out. This is how you do the bending. First, you need to analyze the shear. You do areas, okay? So 240 times 100, that is 24,000. And that is because we're underneath 0, right? It's a negative 100, so this is negative. Hopefully you can see that. That's negative. Same thing here, 240 times 500, right? You're just taking the area of the square. That's gonna give you 120,000. And because we're above 0, this is gonna be a positive sign, okay? Positive 120,000, negative 24,000. Let me show you what that means on the moment diagram. So to do the moment diagram, first you have to see what moments are acting on it. In this case, MA is a moment, right? Remember? M1 was 96,500. So that's a moment acting on the diagram. M2 was 0, M3 was 0. So those aren't, nothing's acting, I mean, M1's the only one acting on the diagram is what I'm trying to say, okay? Everything else is gonna be because of the shear, if that makes sense. So this is just integrals, okay? Remember integrals. This is a negative, pretend this is like a function, right? This is negative 5x. If this is negative 5x, this is y is equal to negative 5. Let's go back to basic, like, calculus, right? When y is equal to negative 5, what's the integral? Well, negative 5x, right? So that's what happens. This 240,000 is a negative. So the integral of a straight line, it's either going to go like this, or it's either going to go like this, right? It's an integral. But because it's negative, we know this is going to be the one we're dealing with, okay? Let's go back here. There was a moment acting, so it's going to push us up or down. It was positive 96,500, okay? So that's going to, because it's counterclockwise, you might think, oh, it's positive, it brings you up. That's not the case. For counterclockwise on the diagram, it brings you down, okay? So we're going to be at right here, negative 96,500. This is in pound inch. You got to label these because your professor will ding you, just by the way. Negative 96,500, this is our starting point. Because at M1, that's what was acting at node 1, 96,500. So it brings you down. And again, this is a positive because it's counterclockwise, but when you're here, it's a negative. You got to remember that, okay? That's real important. That's going to mess you up. If you put it up here, you're screwed. And you know you're going to be screwed, watch, when you do this method. 24,000 is in the negative direction. So that means it's gonna, the shear, as it's going through the 240 inches, you're increasing and bending, okay? So for every inch, you're adding negative 100 pounds, okay? So 1 inch, negative 100, 2 inches, negative 200, 300, 400, until you get to the middle of the beam when something happens. So from here to here, it's a straight line. It's a straight line because it's the integral, remember? This is a negative 5x, or negative 5. So when you integrate, it's negative 5x. So that's why it becomes a slope line, okay? 24,000 plus 96,500. Well, it's not plus, but 2 negatives, right? It's going to bring you to negative 120,000. Okay? We're at negative 120 here. Nothing happens, but you do have a positive slope. So in this case, now imagine our function was 5. Y is equal to 5, right? But when you integrate it, now you're going to get this one right here because you're a positive. You're above the 0. So now you're going to have this relationship, and it's going to be 120,000. So from here to here, you're going to go back to 0. Boom. I hope that made sense. This is how you do these shear and bending diagrams, and it's real easy to mess up. But this is what the bending diagram looks like. So as an engineer, you know, you just did this, and you're probably wondering, well, what the hell did I just do? Why did I just do it? What the hell am I doing? I'm just a student at my little, you know what I'm saying, Harvard University or whatever you're doing, right? What the hell did I just do? The whole point of this problem was, look, they gave you an E and an I. So that means if you have an E, that means you have a material. 30 times 10 to the 6. I think that's steel. I can't remember. Steel or aluminum. I get them confused. Doesn't matter. They gave you a material, so you know E. I, they gave you I. It's a cross section. So you know the cross section's moment of inertia, okay? So because of that, that means you already have the design made. It could be an I-beam, it could be a circular beam. I don't know what it doesn't tell you, right? But they do give you an I and an E. That means you already have material and you already have your cross section. All this that you found, right? Displacements, angle of rotations, right? Forces, reactions, all that good stuff. It's telling you what your system is experiencing. It's telling you, hey, look, the max moment that you're ever going to have on this beam is right at the center, and it's 120,000 negative. Okay, in this case, negative or positive doesn't really matter. Sometimes, I'm not sure what your application is, but for the most part, it shouldn't really matter. In this case, 500 pounds of shear is your max. So when you're designing things, I mean, you're going to see it. You're going to be like, oh shit, this section is experiencing 500 pounds. I got to design that web of that I-beam, if it's an I-beam, or whatever the beam is. I got to design it to withstand 500 pounds of shear. This side is only getting 100, right? Negative 100. This one doesn't have to be as critically as designed as this one. This has to be a beefier web to support that 500 shear flow going through it. Shear, right? The moment is your caps. So in an I-beam, the top flange and the bottom flange, right? I-beam has two flanges, the top one and the bottom one. 120,000 is resisted by those caps. They're called caps. So you have to design those caps thick enough to withstand 120,000 pounds inches. Okay? And you know, as an engineer, you found this number and you found these shear numbers, these critical numbers. You have to design those cross sections. In this case, sounds like they already did. So this problem is more like a check. Hey, let's check if it works kind of thing. And I mean, but that's going too into it. That's giving you guys an idea of why they tell you to do these problems to begin with. Hopefully that kind of clears it up. But let me just show you the solution in a much neater format. Boundary conditions, global stiffness matrix, cross out all your zeros. In this case, you have two of them. Boom, boom. Equations. Yeah, right. Same thing I did. You already heard me say it. Your reactions, all that good stuff. I checked it. Boom. Forces in each element. Those are the system. I mean, I didn't show you these equations here, but here they are in case you were curious. These are the values you get. There's your shear and bending. That's all it is, okay? Oh, I put kip inch. It doesn't really matter. Pound inch. On this one, I put 96,000 and 120,000. Same thing, right? But yeah, that's all it is, okay? So I hope that helped. Let me know if it did. Comment, do all that good stuff you already know. Thank you, guys.